Today we study C8, a scalar product, which is also called the dot product. We explore two-dimensional Euclidean space, which is the vector space. We usually put the superscript 2 to denote the dimensions of a vector space. So this dimension is a mathematical dimension, the number of linearly independent vectors available in a vector space. Okay, so two-dimensional Euclidean space is equivalent to the two-dimensional vector space. In that case, previously we studied the one-dimensional vector space that can be represented by just a straight line, the number line. But in two-dimensional case, we introduce two orthogonal perpendicular to axis, a convenient choice for the basis vector is a unit basis vector that are perpendicular to each other. So that is the E1 along the x-axis and E2 hat along the y-axis. By the way, before we begin, we just define the scalar product any two vectors. In two-dimensional space, we have two arrows sharing the tail. So let me say it is A and the other is B. We say the length of this vector is called the magnitude, and the vector has a magnitude and direction. And as you know, on a plane, you can define the angle between the two straight lines. So the angle between the two vectors can be either this theta or this. That is a 2 pi minus theta. However, we can always distinguish these two except for the case they are opposite. Theta, pi minus theta. They become equal. If you have two angles that has different values, then you always can choose a smaller value for these two angles, a theta and a 2 pi minus theta. Okay, so we define the scalar product between two vectors in this manner. Magnitude of a vector multiplied by the magnitude of the other vector and cosine of this angle between the two vectors. If I have theta is 0, then it is 1. Therefore, in that case, the same vector, for example, a vector scalar product with itself, that is magnitude squared cosine 0, that is a magnitude squared. Therefore, magnitude of vector is nothing but, because it is a positive definite, and this one is also positive, so we do not have plus minus. The magnitude of a vector is nothing but the square root of the self-scalar product. Okay. Once I have a vector, it is convenient to introduce a unit vector parallel to its own direction. The easy way to find a unit vector is multiply a scalar that is a reciprocal of the magnitude of this vector. Simple. We have a completeness relation in one dimension. If I have a vector, this vector can always be expressed as a vector, unit vector multiplied by something. That unit vector is parallel to this A, so what we have chosen is this unit vector, A vector divided by its own magnitude. In that case, we know A hat dot A hat, it is nothing but 1. Why? The magnitude of this is 1, magnitude of this is 1, and cosine 0. So 1, 1, 1. That's 1. Haha. Therefore, we can construct this very simple expression. Any vector can be expressed as a multiplication of a unit vector along that direction multiplied by its component. Okay, so this is completeness. Why complete? We do not lose any small part, any tiny part of this vector. This expression is completely reproducing the original vector. That's the reason why we say completeness relation. And if it is in one dimension, this only a single basis is enough to reproduce any vector along that direction or opposite. If we have two vectors and they are collinear, collinear means collinear, it is the same as a parallel. Anti-collinear is that's opposite. Anti-parallel, same words. If there is a scalar lambda, haha, so they are just scalar multiple of A vector is B. So we say in that case, we say it is linearly dependent upon each other. In general, any two vectors are called linearly independent. Independent only if the coefficients of the two should be 0. And after that, we add them up to find out 0. This is the only solution. That case, we say they are linearly independent. Linearly dependent set is if something multiplied by A and something multiplied by B equals a 0 vector, even though either X or Y, at least one, is non-zero, then we say they are linearly dependent. So what we call dimension of a vector space, that is a mathematical realization of the Euclidean space. The number of linearly independent vectors is very important. In one dimension, such a linearly independent vector is only one. In two dimensions, there are two. Force F is collinear to the acceleration. Why? Force is defined by mass times double derivative of position vector, that is called acceleration. Single derivative is velocity. This is a scalar. Scalar doesn't change the direction. Sure, if this scalar is negative, then it can change the direction in opposite sense, but changing the direction in opposite sense does not mean they are linearly independent. Just like that, opposite direction is just a linearly dependent one. Sure, in classical mechanics and Newtonian mechanics, any physics, there is no particle with negative mass. So force and acceleration, they are collinear. Therefore, they are linearly dependent. Velocity, accelerations are always collinear to x in one-dimensional Euclidean space. That's fine. However, in 2 or 3 dimensions, they are not. Because, for example, velocity is the difference of the position. That is called the displacement divided by time difference. In one dimension, this one is linearly dependent upon this. However, in 2 dimensions, for example, this position, x at time t and x at t plus delta t. So these 2 vectors are linearly independent because I cannot multiply any number. If I multiply any number to this vector, I can move around on a straight line. I cannot reproduce this. To reproduce this, I have to find another vector that is not parallel to this. So find out the component to reproduce this value. So these 2 vectors in 2 or 3 dimensions, they are linearly independent. If I have 2 vectors, then in 2 dimensions, we have only a single angle. However, let's see. We have 2 vectors in 3-dimensional space. In 3-dimensional space, we usually say the angle between the 2 axes is called a polar angle. Polar angle. The reason why we use this polar is a pole, North Pole and South Pole. And angle, theta is measured from North Pole, okay? And we have polaris and angle from here. But usually we have longitude. In geography, we use longitude. So 0 is here, equator is here, but we usually measure this polar angle from the equator. It's a positive sense and negative sense for the northern hemisphere and the southern hemisphere. In physics and astronomy, we prefer the plus z-axis, that is along toward the North Pole. From here, we measure this angle. You can find this one if you increase the angle and you arrive there and go further. What happens? They are opposite to each other. In addition, any point in here, this I have written a vector b, and we can keep this angle between A and B to be theta, but still I can rotate this one about the axis parallel to A. What happens? This B can rotate. This tip can rotate on a circle. Okay, so even though I have a polar angle between the 2 vectors, in 3-dimensional geometry, there are variable ways to reproduce the angle between A and B. So this freedom is called azimuthal angle. And we know our Earth is rotating about the z-axis counterclockwise. Therefore, this is called the polar angle, and the Earth's self-rotation represents a circle, and there is a cone. Haha. To find out the point on a spherical surface, what I need is the angle from the North Pole, that is called the polar angle. And just like what we used is we use two coordinates, longitude and latitude. Okay, two coordinates. So these are related to latitude, and these are related to longitude. And longitude is related to the azimuthal angle, that is 360 degrees, but we do not use the degrees. This is not a scientific notation. It is good to use dimensionless angle, 2 pi. Okay, so it runs from phi. This note, we use the phi for the azimuthal angle, theta for the polar angle. Next, we consider two vectors. We repeat considering two vectors. I told you the angle between them, the small angle between the two vectors, is called theta. From middle school, we learned we have a right triangle. This is a R hypotenuse and A and B. And we define this one to be the angle. And actually, this is the azimuthal angle. If I choose the x-axis along this direction, y-axis along this direction, and this coordinate will be A, comma, B. And we can draw a circle of radius r, then A is r cosine theta, and B equals r sine theta. Everybody knows about this. Okay, this is what we know already, but let us look into this. Let us reproduce what we learned more than almost 10 years on the XY plane. So A can be divided into two pieces. B. B can be divided into two pieces. We have A in here, A is here, and B is there. This is A, and I'd like to express this vector B in terms of the basis vector that is parallel to this and perpendicular to this. Okay, in that case, what I have done is just move this one here and let the x-axis, let this side A to be on the x-axis. And this B is nothing but this. So let's erase this. Then this vector B is this vector, and I can decompose into two pieces, sum of these two components, and they are perpendicular to each other to make a resultant vector equal to B. Then, because this angle is theta, we have this magnitude B cosine, and this is B sine. Okay, so finally, we arrive at the point that A is sum of, B equals sum of B parallel plus B perpendicular. This one is a parallel to A. This one is perpendicular to A. This is A, parallel to A, perpendicular to A. We can also decompose vector A relative to vector B, and this is the parallel component relative to B, and this is a perpendicular component relative to B. The parallel component can be easily read off by making use of the scalar product we just have defined. This is what we have considered. Okay, in here, what you find is a scalar product of two vectors that they are perpendicular to each other. This parallel and perp, parallel and perp, they are perpendicular to each other. Perpendicular to each other, cosine half of pi equals 0. So they are all 0. As a result, if I compute the scalar product, this is a B parallel plus a B perpendicular. B perpendicular is a perpendicular to A, therefore, this one does not contribute. In here, A parallel plus A perp dot B, this guy is perpendicular to B, so this one does not contribute. And both of them are A dot B. Both of them are A dot B. One step further, I can rewrite this one to be B perp and B parallel. Aha! What I find is a B perp is a perpendicular to A. But this is A parallel. So let us stop here. The convenient expression is this. What we have found is this. And then next step, this one was A, and this is the direction of B, and A parallel and A perp. And magnitudes are angle dependent on the angle, that is A cosine or B cosine. That's fine. Therefore, A parallel, that is a parallel component along B, magnitude is copied. Magnitude is A absolute value multiplied by cosine theta. And I need a unit vector along B to represent this. In a similar manner, B parallel, that is a parallel component of B, that is a parallel to A. So I have the unit vector and the magnitude. Why don't we compute A parallel and B parallel? A parallel is here. This is A, and A parallel is this. And B parallel is actually not parallel to B, but parallel to A. So B parallel is component of this, and B perpendicular is this. So B parallel has the magnitude smaller than B by a factor of cosine. So this guy brings a cosine, and this guy brings a cosine, another cosine, and the B hat dot A hat, as is written in here, we have another cosine. So looks complicated. A parallel, that is a parallel component of A parallel to B. So, and their scalar product is not the AB cosine, but instead it is a cosine cube. So it's a kind of fun. Next, A and B are linearly independent. Oh, By the way, we have only 5 minutes. So let me pass. It is a repetition of a previous one. Any vector, this is B, relative to A. If I have A is here, B can be decomposed into two components. And there is, if it is a right angle, it is a rectangle. And let's say it is a B parallel and B perp. Then they are perpendicular to each other. If you look at this figure, how can I obtain this vector? This is a B. This is a B perp. If I want to obtain this guy, then what I need to do is, how can I obtain this? I need to flip this direction. Flip this direction. So minus a B perp. So this one is the same as this. In this manner, B perp is B minus B parallel, and B parallel is B minus B perp. But perp is easy to compute. Parallel is easy to compute according to the one-dimensional completeness relation. One-dimensional completeness relation. Parallel component can be read off by taking the scalar product with the unit vector along that direction and then multiplied by the unit vector. So if I subtract this parallel component, B, and if I subtract a parallel component, subtract this one, then what I get is perpendicular component. So if I have two perpendicular vectors, then any two non-vanishing vectors that are perpendicular to each other must be linearly independent. For example, we have x coordinate, y coordinate, right triangle. These two sides are not vanishing, then this one can be or can only be expressed in terms of x comma y, and these two coordinates are non-zero. Okay, so this one means 1 comma 0 and 0 comma 1, they are linearly independent. If I multiply two numbers and add them up, and they become 0 comma 0, only if these two are both 0. That is the reason why we use this linearly independent set of basis vector, because we have chosen in this linearly independent set as a basis vector, our coordinates are uniquely defined, and you have never had some problem of a multiple solution for this x comma y in the two-dimensional plane. Okay, so we can now obtain any parallel component. And if I subtract this part from a vector, I can always choose the perpendicular component, and these two are linearly independent as long as they are not zero vectors. This is the reason why we use this Cartesian coordinate system, and Cartesian coordinate system has a unit vector along the x-axis and y-axis. By the way, okay. Finally, this is to show in 3 dimension to choose the linearly independent set of 3 vectors. For example, first I have chosen an arbitrary vector that is now called E3 hat, and I remove that parallel component, then what I get is the component perpendicular to, I have a cone, some direction. This is an arbitrary vector, and parallel component is this. If I subtract this from this vector, what I get is a vector that is on a circle, and that is perpendicular to this. So this is a cone and base of a cone, and any point on the rim of the base of this cone can be parameterized by these two unit vectors. So E1, E2, and E3. So E1, E2, E3. This is finally obtained as the convenient set of unit basis vectors. Okay, so I think you can go ahead with this material for the 2 and 3 dimensions without any problem, but don't forget to study this figure. We will have many problems regarding this figure. Okay, that's it for today. Thank you.